We've reached the last video in chapter 14. In this video, we're going to be looking at reaction mechanisms, which is section 14.6, and catalyst, which is section 14.7. For reaction mechanisms, we want to look at what is happening on a molecular level. In other words, what molecules are running into each other during the course of a reaction, and in which order are they running into each other. And so it is a description of what is going on. It tells us a sequence of events. All right. We will find that there are two types of mechanisms. The first type is called a concerted mechanism. Concerted mechanisms are single-step mechanisms. That's where molecules come together and then they get converted into something else. There's not any like it breaks apart and makes a new thing and then that reacts with something else. It's not a sequence of things. It is just a single step. So we call that a concerted mechanism or single step mechanism. The other type is called a stepwise mechanism, which is more than one step. So it's a series of individual discrete steps. These individual steps we will refer to as elementary reactions, or sometimes we'll simply call them elementary processes because sometimes these things don't technically qualify as an elementary reaction, so we just call it a process. In any case, an elementary process includes elementary reactions, so we're all good. So each step is called an elementary reaction. We want to look at how it is that if we know what the elementary reaction step is, we can write the rate law for that step. So if you know what the elementary process is, you can write the rate law for that step simply by looking at the stoichiometry. Now you'll see here I have a big disclaimer. Note, you cannot do this with overall reactions. You can only do this with elementary processes. If you know you have a one-step reaction, then yes, you can do this with an overall reaction. But usually you don't know that. So I'm warning you, don't do this with overall reactions. Only do this when you know you have an elementary reaction step. So this is how it works. If we only have one molecule that is required for an elementary process, then we call that a first order process, and we will find that the rate law will be first order. We use a word that's called molecularity, and the molecularity just describes how many molecules are present here in that elementary process, or how many reactant molecules are present. So for first order, we call it unimolecular. So the molecularity is just unimolecular, bimolecular, and termolecular. So unimolecular means one. Bimolecular, here's an example where we have two of the same thing. You'll see that it is second order with respect to A and second order overall. So that's bimolecular. We can also have where we have two different things. So A and B, it would be first order with respect to A, first order with respect to B, second order overall. And then here we've got some unusual kind of exotic examples that we refer to as termolecular. It's possible to have three of the same thing. So A, and A, that would be third order with respect to A, third order overall. AAB, it'd be second order with respect to B, A, first order with respect to B, third order overall. And for three different things, first order with respect to each and third order overall. Now, before you get all excited about termolecular reactions, I'm going to warn you, don't get excited about termolecular reactions. And the reason, well, if you find one, yes, get excited. But it's really hard to prove that you have a true termolecular elementary reaction. And in fact, it's just so rare for it to happen. It is just so rare. So we'll find that unimolecular and bimolecular reactions are very, very common. We'll see these quite a bit. Termolecular reactions Well, all right, let me explain what has to happen. In order to get a termolecular reaction to occur, you need to have 3 molecules show up at the same place at the same time and have enough energy so that they can react. And on top of that, they need to have the correct orientation so that they can react. That can be a real trick. It can be very, very difficult to do that. Statistically, it's just not very likely that 3 things are going to run into each other at the same time. It's a 3-body problem, and 3-body problems are very difficult. So we're going to say, just using Occam's razor, which is usually it's the simplest case, if you find that you have an elementary reaction step that is termolecular, it probably isn't. It's probably like 2 steps that appears to be a termolecular reaction. So for purposes of this class, we're going to say that termolecular reactions are so rare as to not really exist. I'm not saying that they don't exist. I'm just saying in all of the years that I've been a chemist, I don't know that I've ever seen one for sure that I could say, yes, that's a termolecular elementary reaction step. All right. So now what we want to do is number 61. 61 is pretty easy. It's just identifying the rate law for elementary reaction steps. All right, so we've got what is the molecularity for each. To do this, we just look at what molecules, how many molecules are over on the left side of the equation. So for this first one, we've got Cl2, and it gives us 2Cl. Well, since we've got Cl2 on the left side of the equation, that's only 1 molecule, and so we're going to say that is unimolecular. And since it's unimolecular, we should have a first order element or first order rate law. So rate is equal to K times the concentration of Cl2. And that's it. All right, for this one, so again, we just need to look on the left side and see how many things are there. Well, we've got hypochlorite and water. They're both a gas phase here. So we're going to say that is bimolecular, because there are 2 molecules. And that means we should have a second order rate law here. So rate is equal to K times the concentration of OCl minus times the concentration of H2O. All right, finally, we see this reaction over and over again. This one will show up here, and it's going to show up in a similar way in the next chapter, or in the next section. So, so here we got NO plus Cl2 gives us NoCl2. All right, if we look, there's 2 things on the left, so that must be bimolecular. All right, and then our rate is equal to K times the concentration of NO times the concentration of Cl2. And that's it. So that's how we write rate laws for elementary reactions. Again, I want to caution you, you can only write rate laws using stoichiometry if you know for sure it's an elementary reaction. If you have an overall reaction, you cannot do this. So if you have an overall reaction, you cannot do this. Okay. So we have a couple of rules that we're going to set up here when we're doing multi-step mechanisms. And I used to not have this page, but I put it in there because I want everybody to understand. I want everybody to understand exactly what our limitations are when we're doing this, and so our ground rules for doing this. The very first thing, and this may seem obvious, but I want to make sure that everybody gets this, is that the sum of all the individual steps in a mechanism have to give the correct stoichiometry for the overall reaction. So when you add the individual steps, it has to add up to the overall reaction. So that is an important factor. If that's not true, then your mechanism is invalid. The individual steps in a mechanism have to be balanced. And this seems obvious, but sometimes you see people write mechanisms and they're not balanced, and that means they are not valid. So make sure that your individual steps are balanced. Now, for the ones that we're going to do, I'm going to give you the individual steps and they will be balanced. All right. Sometimes in the course of a reaction, there will be a substance in the mechanism that is not a reactant, it's not a product, and it's not a catalyst. It is what we refer to as an intermediate. It is something that is formed in one step and then used up in another step. Well, anytime we have an intermediate, the intermediate, if it's formed in one step, it must be consumed in some subsequent step. We can't have intermediates just showing up all over the place and not get used up. Otherwise, we would call them products. So intermediates, we must account for them and make sure that if one's created, then another one is used up. Otherwise, it is not an intermediate. We'll also find that since intermediates are not reactants, they're not products, they're not something that we put in there, we don't know how much is there, we can't have an intermediate in the overall rate law. So we cannot have an intermediate in the overall rate law. That is a big deal. All right, if we have a catalyst present in the reaction, now we haven't talked about catalyst yet, but we will when we get to section 7. If we have a catalyst can be used in one step, but it needs to be regenerated in a subsequent step. We can't have a catalyst that is used in one step and then not regenerated. If it's not regenerated, it's not a catalyst. It's just a reactant. And then finally, we're going to derive our rate law from the rate law for the rate determining step. So when we write down the rate law for the rate determining step, that will dictate what our rate law is. All right, and I'll show you how that works here in just a bit. So next, rate determining step. So most of the time, if we've got a multi-step mechanism, 2 or more steps, one of those steps is going to be somewhat slower than the other, so usually significantly slower. Now, it is possible that you could have 2 steps and that both steps have the same rate, but it's unlikely. It's unlikely. And to explain this, and we call whatever that slowest step is, we call that the rate determining step. And so our overall reaction can't be faster than that slow rate determining step. Now, to explain this, I'm going to use an analogy, and unfortunately, this is a somewhat dated analogy, but I'm going to see if I can modify this analogy and maybe make it a little bit better than it used to be. So here we've got a toll road, and you guys are familiar with toll roads. Living in the greater Dallas area, we love toll roads around here. Well, I don't know if we love them, but we don't like paying for roads with taxes, so toll roads it is. All right, so here we've got cars that are at position 1. We're going to call them reactants here. And that we've got 2 steps. There's a step here that's a toll plaza and another toll plaza. And it used to be, back in the old days, when we had toll... All right, I'm doing my old man voice. So back in the old days when we had toll roads, we didn't have these... What do you call it? We didn't have toll tags, and we didn't have even the change baskets. If you went on a toll road, you had to stop at a booth, and there was an actual physical person there. You had to give them money, and then they would give you change, and you could go along your merry way on your toll road. And so that's kind of what's happening here. You'll notice all the cars are kind of piled up here because they're waiting to get into those booths. There are some booths that are like that at the airport, although they are becoming more, toll tag and that kind of stuff as well. So things are getting more automated. So you'll see here, let's just say that here we've got all people manning these, and so that means that each one of those, it's going to just take more time to get through it. And then just right up ahead, not very much further, you see that there is another toll booth, but this time it is electronic, and so it just scans either your license plate or your toll tag, and you drive right through. You don't even really have to slow down that much. You just have to slow down enough to make sure you don't run into anything. Well, that would be a fast reaction, and this would be slow. And given the approximate distances here, you would say that the amount of time that it takes you to get from point 1 over here to point 3 is going to be largely determined by how long you sit in that line. And so the slow step is the rate determining step. All right, so that is an example of what would be a slow first step. Now, if you turned it around so that in Toll Plaza A, you had all the toll tags that were really, really fast, and over here in Toll Plaza B, you had people so that everybody had to stop and give change and all that, then that would be a slow second step. So we're going to look at one of each of these examples. We'll start with a slow first step or slow initial step. All right, so we're going to start with a slow initial step. Here is our overall reaction. NO2 plus CO gives us NO plus CO2. So that is our overall reaction. If this reaction had a concerted mechanism, in other words, if it had a single step mechanism where there's just a single elementary reaction that is that mechanism, then this would be the rate law, right? Because if this were an elementary reaction, it would be K times the concentration of this reactant, and since its coefficient is 1, it'd be raised to the first power, and carbon monoxide, again, also to the first power. So that would be our rate law if we had a single step mechanism, all right? However, when we do the experiments and do the math, we'll find that this is the actual rate law, that the rate is equal to K, and it's our observed rate constant, K times the concentration of NO2 squared. All right, so it is a second order reaction, but it's second order with respect to nitrogen dioxide. Well, there's a couple of things that, a couple of conclusions we can come to about this. If we knew if it were a one-step reaction, this would be the rate law. Since this is not the rate law, it's actually this. That means it's not a one-step reaction. So the fact that it is not the same as what it would be if it were one step, that implies that we must have a stepwise mechanism. Now, we don't know how many steps. It could be 2, 3, 100 steps, but we know that it is not a one-step reaction. The other thing that's kind of interesting here is that carbon monoxide is a reactant, but you'll notice that it doesn't show up in the rate law. Well, technically what that means is that the order with respect to carbon monoxide is 0 order. It means that we can change the concentration of carbon monoxide, but it doesn't change the rate of the reaction, which that's kind of interesting. So the rate of the reaction is independent of how much carbon monoxide is there. So again, we would say that the order of the reaction is 0 order with respect to carbon monoxide. Okay, so now we need to have a plausible mechanism for this. Now, mechanisms are very difficult to prove absolutely, but it is possible to determine whether a mechanism is consistent with our actual observations. And so we're going to determine, is a mechanism plausible? So here is a proposed mechanism with a slow initial step. So here is a mechanism with a slow initial step. All right, so again, I've rewritten the overall reaction so you can clearly see what the reactants and products are. Here is our first step, and in the first step we've got NO2 plus NO2 gives us NO3 plus NO, and you'll see that it says the word slow by it, indicating that that is our rate determining step. Our proposed second step is that NO3 reacts with CO to give us NO2 and CO2. Now, remember our requirements. Our requirements for a mechanism is, one, that the sum of these reactions has to add up to the overall reaction. Well, we'll see that we've got NO2, NO2, and then one NO2 on the right. So one of those NO2s cancels out, so NO2 is good. NO3 and NO3. NO3 is not a reactant, it's not a product, it must be an intermediate. So NO3 cancels out. NO is on the right side, and then CO2 is on the right side, and then CO is on the left side. So everything, it does add up to give us this reaction. So that meets the requirement for that. It also meets the requirement because we did have an intermediate present, so it meets that requirement. And since it meets that requirement, you'll see that the intermediate is formed in one step and it's used up in a subsequent step. So this appears to meet our requirements for multi-step mechanisms. So the NO3 intermediate is consumed in the second step. All right. And the rate law for that first step would be this. Now, one of the cool things about when you have a slow first step, whatever the rate law for that slow first step is, that's going to be the rate law for the overall reaction. So here our rate law for the first step, so rate law for step 1 is K1, which is just our rate constant for the first step, times the concentration of NO2 squared. And so that is going to be our slow step, and you'll see again it forms NO3 plus NO. And then once that NO3 is formed, it reacts quite quickly with the carbon monoxide to give us the carbon dioxide. So our proposed mechanism has this as a rate law, and this is our observed rate law. And since those are the same, that means that this proposed mechanism is consistent with the overall observations. And then finally, we mentioned this a little bit ago, but because carbon monoxide is not involved in the slow rate determining step, it does not appear in the rate law. And so there is, it doesn't show up in our rate law. It's actually zero order, if we will. All right, so let's look at number 67. 67 is pretty easy. All right, so here is number 67. And on this one, we've got, so 2NO plus Cl2 gives us 2NoCl. It obeys the rate law. Rate is equal to K times concentration of NO squared times concentration of Cl2. And then here we have a mechanism that has been proposed for the reaction. So NO plus Cl2 gives us NoCl2, and then NoCl2 plus NO gives us 2NoCl. Okay, so it does not tell us which step is the slow step. So it does not tell us which step is the slow step. But it does ask, what would be the rate law if the first step were rate determining? Well, if the first step is rate determining, then whatever the rate law for that first step is, that should be the rate law for our overall reaction. So we can determine what this is going to be. It'll be equal to K times the concentration of NO times the concentration of Cl2. And that would give us a rate law that is this. All right, so this would be the rate law if the first step was rate determining. We come up here, this is our actual rate law. It's NO squared times concentration of Cl2. That's a third order overall rate law, but we only have a second order rate law if the first step is rate determining. So based on this observed, what can we conclude about the relative rates? Well, if the first step were rate determining, if it were the slow step, this would be the rate law. Since that's not the rate law, the first step is not rate determining. All right, so step 1 is not rate determining. That means that step 2 must be our slow step. So step 2 must be our slow step. Again, if the first step were slow, it would be this. Since it's not this, that first step can't be the slow step. It can't be rate determining. And that's all there is to number 67. We're not going to actually figure out what the overall mechanism is. Well, we sort of have it now. We know the second step is slow. But I am going to show you how this works with a slightly different example here in just a moment. Okay. I now just briefly want to look at multi-step reaction coordinate diagrams. And because there's extra information. Previously, when we looked at a reaction coordinate diagram, we just had one hump. But when we have multiple steps, we're going to have multiple humps in our diagram. And so it looks like maybe a camel underneath a blanket. Okay. So each step is an elementary reaction step. So each transition state represents an elementary reaction step. So this is a step and this is a step. So you can tell that this is a two-step reaction. The intermediate has a relative a minimum in between the two transition states. So here we've got an intermediate in between those two transition states. The slow step is the step with the largest activation energy. And the activation energy is the difference between where did you start before that step and the transition state. So our first step, the activation energy, is going to be the difference between our reactant and this first transition state, which is a huge number. The activation energy for the second step is going to be the difference between the intermediate and this second transition state, and that's a little tiny activation energy. So the bigger the activation energy, the slower that step. So step one will be our rate determining step. Finally, intermediates are sometimes stable. They're sort of semi-stable relative to the transition state. And so those intermediates can be difficult to observe, but it is technically possible if you're clever to get an intermediate, to isolate it and actually observe that intermediate. All right, we're going to look at number 64, and good news, we are almost done with this chapter. All right, so here is number 64. This is a pretty easy question. And in fact, if I had not shown you that page before, I bet you still could have figured out the answer to this. So how many elementary reactions are in this reaction mechanism? Well, when we look at that reaction mechanism, we'll see two humps. So there are two steps. All right, are two elementary reactions. How many intermediates are formed? Well, the intermediates are the relative minimums here. So this is the intermediate. So we'll say one intermediate. Which step is rate determining? Again, we need to look at the activation energy and the difference between where it starts and where that transition state is. So our first one has an activation energy that is this much. Our second step is between there and there. And you can clearly see that second step has a larger activation energy. So the second step should be the rate determining step. And then finally, is the overall reaction exothermic or endothermic? Well, if it's going down, that means the difference between this and this, that energy is released into the surroundings. And so since it's going down, that means it is exothermic. So it's exothermic because it is going down. The one that we had on the previous, on the presentation, this one happened to be endothermic because it was going up. All right, we are close to getting done here. Very, very close. So now for a fast initial step. So here we've got the reaction 2NO plus Br2 gives us 2NO-Br. All right. We'll find that when you do experiments for this, we'll get an observed rate law that looks like this. So rate observed is equal to K times the concentration of NO squared times the concentration of Br2. Now, I think you guys realize at this point that when you look at this, this is a third order rate law. So 2 plus 1, that's a third order rate law. And so if this reaction were a concerted reaction, then that would be the rate law. So that technically could be a possibility. But I've already mentioned that termolecular elementary reactions are very, very rare. So rare that we're going to say it probably didn't happen that way. So usually what happens is there's at least 2 steps. But this suggests a multi-step mechanism. So even though that would work, term molecular reactions are just unlikely. So we're going to say it's probably a multi-step mechanism. So I'm going to show you a proposed mechanism for this reaction. Again, I'm going to show you the reaction again up on top. So 2NO plus Br2 gives us 2NOBr, and this is our proposed mechanism. Our first step is a fast step. You may already have noticed something different about this reaction. One is that it's got the double arrows. We're going to talk about that here in just a moment. So NO plus Br2 gives us NOBr2. And then NOBr2 can in turn react with NO to give us 2NOBr. Now, we need to make sure that it meets the requirements for a multi-step mechanism. One, that the reactions have to add together to give us our overall reaction. So if we add these together, we have NO plus Br2 plus NOBr2. And then over on this side, we have NOBr2, so that cancels out, and that looks like it is an intermediate. And then we get 2NOBr. So it does add together to give us this overall equation. So it meets that requirement. The requirement about the intermediate, this intermediate is produced in step 1 and used up in step 2. So yes, it meets that requirement as well. So the other thing is that the rate law will be dictated by the rate law for the slow step. So our slow step is the second step, and if we write the rate law for that slow second step, we're going to get this, that rate 2 is equal to K2 times the concentration of NOBr2 times the concentration of NO. Right now, it looks like we're on a great path. We're almost done, right? Not quite. Not quite. We have a little bit left to go here. And that little bit left to go is we can't leave our rate law like this. And the reason we can't leave the rate law like this is because you will see that it has an intermediate present in the reaction. And we are not allowed to have an intermediate present in our rate law. So intermediates cannot be in the overall rate law. They can be in individual step rate laws, but they cannot be in the overall rate law. So we need to find something that we can put in place of NOBr2. So we want to find a substitute for NOBr2. Now you'll notice I still have the steps up here. We want to write the rate law for all 3 steps. Now, for those of you who are good at counting, you may look at this and say, that looks like 2 steps. It does not look like 3 steps. I don't know what you're talking about. But you'll see that the first step has both a forward direction and a reverse direction. And we can write the rate law for the forward of the first step and for the reverse of the first step. Since the first step is step 1, we're going to call it the forward rate 1 and the reverse rate negative 1. So the rate law for the forward step, again, we just look at the stoichiometry for the reactants. We have 1 mole of NO, 1 mole of Br2, and so we'll have rate 1 is equal to K1 times concentration of NO times concentration of Br2. For the reverse step, we only have one thing over there, so it will be first order. And so there, rate negative 1 will be equal to K negative 1 times the concentration of NOBr2. All right. And then finally, for our slow step, we've got this. Now, I highlighted in red our intermediate because we can't have that intermediate in our overall rate law. So we can't have that intermediate there. We need to come up with a way to get rid of this. And here is how we're going to do it. We're going to do it by making an assumption. This assumption is not perfect. So this assumption is not perfect, but it is a pretty good assumption. And the assumption is that that first step is so fast that most of the time when we take NO and Br2 and convert it into NOBr2, most of those molecules of NOBr2 will break apart and go back to NO and Br2. So it's a very, very fast step, and most of that NOBr2 does not go on forward to make NOBr to combine with NO to give us the 2-NOBr. So this is our assumption, is that the rate of the forward for the first step is equal to the rate of the reverse for the first step. That is our assumption. So the rate for the forward is equal to the rate for the reverse. Okay, so now let me show you how we use this. So over here, I've got rate 2, and again, we're trying to find something that we can substitute in place of NOBr2. I mentioned that rate 1 is equal to rate -1, and with that, we can just write down the rate laws for rate 1 and rate -1. So here's rate 1, there's rate -1. And since these are now equal to each other, we can just solve this equation for the concentration of NOBr2. So we'll solve it for the concentration of NOBr2. We'll divide both sides by K-1, and we'll get this. So K1 over K-1 times concentration of NO times concentration of Br2 is equal to NOBr2. Well, now we have something that we can put in place of NOBr2. So we're going to take this whole thing and substitute it in for the NOBr2 over here on the right side, of the page. So when we substitute that in, we'll get K2 times K1 over K-1 times concentration of NO times the concentration of Br2, and then close parentheses, and then concentration of NO. At this point, it's possible to combine a few terms. If you take a constant and multiply it by another constant, you will get a constant. And then if you divide it by yet a third constant, you will still have a constant. So we can take all three of these constants and combine them together into just an overall constant. We can also take the NO that is here and the NO that is there and combine them together to make NO squared. And so now we've got a rate law based on the mechanism that rate is equal to K times concentration of NO squared times concentration of Br2. Well, that is consistent with our observed rate law. And so since that's consistent with our observed rate law, this proposed mechanism is consistent with observation. It means it might be true. Now, proving that it's true is a little bit more complicated, but it might be true. All right, we're going to look at number 94. All right, so here is number 94. And we don't even need that calculator, so we're going to scoot that over. Okay. So the following mechanism has been proposed for the gas phase reaction of chloroform and chlorine. So, so here chlorine breaks apart to give us 2Cl. Chlorine atom plus chloroform gives us HCl plus CCl3. And then Cl plus CCl3 gives us CCl4. So we've got fast, slow, fast. And we want to figure out what the overall reaction is. Now, if you're watching this, at home, and I would encourage you to stop the video and see if you can figure this out before I show you how to do it. Okay, I'm assuming that you just did it, and that you're feeling very proud for having done it. So now what we're going to do is we're going to write the overall reaction. And to do that, I'm just going to put a very light line through, I'm going to put a very light line, I'm going to put it in green, a very light line through things that we cancel out. So things that are identical that we cancel out. So you'll notice that we've got a Cl gas, and then 2Cl gas over here. So I'm going to put a light line through that, and that, and that. So those cancel out. And then we also have a CCl3 here, and that cancels out. And then the things that don't cancel out are Cl2, the CHCl3, HCl, and CCl4. So our overall reaction is going to be Cl2 gas plus CHCl3 gas, and that gives us HCl gas plus CCl4 gas. And that is our overall reaction. Now, what are the intermediates in this mechanism? The intermediates are the things that we just canceled out. So our intermediates are going to be Cl gas and CCl3 gas. It doesn't particularly matter that we've got 2Cl. We're just going to say Cl gas and CCl3 gas are our intermediates. Okay, next, write the rate law for each elementary step, including the reverse of the first step. So the rate law, so we'll do rate 1. Rate 1 is equal to K1 times the concentration of Cl2. All right, and then it says also give the molecularity. So since there's only one molecule there, that one is unimolecular. All right, and then we'll do rate -1. So rate -1 is K -1, and then it's going back. So there's 2 molecules of Cl, so we'll do Cl squared. And since there's 2 of those atoms, that one is bimolecular. All right, step 2. So rate 2 is equal to K2. This one's important because it's the slow step. It's the rate determining step. So rate 2 is equal to K2 times the concentration of Cl times the concentration of CHCl3. All right, that one is also my U got a little out of control there, so we'll try that. Bimolecular. Again, in case you're wondering, I'm recording this late at night because it's quietest, and so sometimes I get a little groggy. All right, so bimolecular, and then finally let's do rate 3. This one's not too terribly important because it's a fast step that's after the slow step, but it is kind of interesting. And we've got 2 things here, so Cl plus CCl3. So we'll do Cl, concentration of Cl times concentration of CCl3. And then that's it for it. And oh yes, it is bimolecular. You'll notice we didn't have any termolecular reactions because termolecular reactions are extremely rare. All right, part D. What is the rate determining step? Well, this is easy. It's the one that has the word slow written by it. So that's our rate determining step, is step 2. So step 2. All right, finally, what is the rate law predicted by this mechanism? Well, here is our rate law for the second step. And since that's rate determining, I'm going to put RDS, meaning it's the rate determining step. So step 2 is our rate determining step. You'll notice that the second step has an intermediate in it, has Cl gas. We cannot have the intermediate in there. So we need to have something that we can put in place of that intermediate. The way that we're going to do that is we're going to say for our first step that the rate of the forward is equal to the rate of the reverse. So we're going to say rate 1 is equal to rate -1. All right, so rate 1, rate -1, that means K1 times the concentration of Cl2 is equal to K-1 times the concentration of Cl squared. We want to solve that for the concentration of Cl. So we'll get, I didn't leave much room here, so we'll get K1 over K-1 times concentration of Cl2 is equal to the concentration of Cl squared. Of course, now we're going to need to take the square root. So we'll get the square root of K1 over K negative 1 times the concentration of Cl2, and that is equal to the concentration of Cl. All right, we're now ready to substitute. So we've got Cl here, and there's Cl is equal to that. So we're going to take that thing that's in the square root sign and put it in place of that Cl. So rate 2 is equal to K2 times the square root of K1 over K negative 1 times concentration of Cl2. And then finally, we'll put CHCl3, concentration of CH. Oh my goodness, I ran out of room. Concentration of CHCl3. All right, that got a little ugly. Sorry about that. Let's simplify this. So we've got a constant times the square root of a constant divided by the square root of another constant. Well, that is a constant. So we're going to say that our rate, and here I'm going to put this in a nice pretty red color, is that our rate is equal to K. And then we've got the square root of chlorine, of Cl2, square root of the concentration of Cl2. Well, another way of writing square roots, so Cl2, is we can write it to the 1/2 power. All right, and then finally, we're going to put concentration of CHCl3. And again, I am just almost completely out of room there, but it all fits in there. Now, I didn't read the hint. It says, what's the rate law predicted by the mechanism? Hint, maybe I did read this. The overall reaction order is not an integer. Well, if you look, the overall order is 1.5, and so the overall order is not an integer. And so that is the answer to that particular one. Okay, well, our video has been going for 46 minutes, so I'm going to stop this video, and then I'll do Catalyst on the next and final video.